We continue talking about line integrals. Now let's look at exact differentials. You remember from previous videos when we talk about line integrals, right? Just a quick review here. You're integrating from one part of a curve to another, right? And if this curve has a length, well, we did not say use L, we use S. This arc length, S, right? The derivative would be that of a tangent to S. And if we cut this curve into more and more parts and add them up, eventually, when you go from A to B, right, and you would have more than one tangents, and you keep adding up the S's, then this, you have the integral from A to B of f of t, the function of that generates the curve, right, or some value, times the length of the curve, ds. That value might be force along a distance and so on, where the distance is s. But you can break the tangent into horizontal and vertical components, right? If you call the horizontal component P and the vertical component Q, then what you have is the integral from A to B of P, the horizontal component, times the change in distance along the horizontal dx, plus the vertical component times the change in distance along the vertical, which is dy. So P dx plus Q dy. Instead of AB, you could have C. So it's integral along a curve of the horizontal component of the force or whatever other function multiplied by the change in distance along the horizontal. Horizontal component would be the x component, alright? The horizontal component of a function of x and y along this, plus the vertical component of our function of x and y times the change in the vertical distance y, alright? Now, here, do you remember this formula? Change in a function is the partial derivative of the function with respect to x times dx plus the partial derivative with respect to f, partial derivative of f with respect to y dy, right? Now, the thing is, you have our dx here and our dx here. The d delta f by delta x, the partial derivative would correspond to the horizontal component here, and this partial derivative with respect to y would correspond to the vertical component here. Alright? Now, suppose you have the function, you have a function of x and y, right? then our P here, which is horizontal, would be equal to delta F by delta X. And our Q here correspond to delta Z. Delta F by delta Y. You see that? Now, here, you remember that this, it was called the total differential of F. Alright? Now, that total differential can also be what you call an exact differential. When you have this case, suppose you differentiate, which is delta F by delta X with respect to Y. Then what you have is delta squared F by delta X delta Y. And suppose you differentiate delta F, or let me rewrite it this way. You have a D by, not D, you have a delta by, or partial by partial Y of partial F by partial X. What you would have then is a delta squared F, partial squared F by partial Y of partial X. And if you differentiate this part with respect to X, then you have a partial with respect to X of partial of F with respect to Y. This would yield partial square of F by partial X partial Y. Now we saw before that the partial square of F by partial Y partial X will always be equal to the partial square of F by partial X partial Y. Right? So here, these, if you consider P to be partial F by partial X, then the partial of P with respect to Y would be equal to, and you consider the partial Q as partial of F by partial Y, the partial of Q with respect to X. You differentiate this with respect to X. Now when that is the case, then you have what is called an exact differential. Right? So the exact differential, if you take this thing P and differentiate it with respect to Y, right, you get a value. If you take Q and differentiate it with respect to X, you will get back that same value. Right? Now, we're going to look at an example of this in our next video. Right? So, I'll see you then.